So today we're going to talk about activation energy. We've looked at potential energy diagrams, but so far we've just considered the general overall shape of the diagram. And there's a little bit more to it than I've actually explained to you so far. So let's consider a reaction. We've got carbon monoxide reacting with nitrogen dioxide to give carbon dioxide and nitrogen monoxide. Now, in basic introductory chemistry, this is how we would have represented the reaction, right? This my reactants turning into my products. And what we learned how to do with potential energy diagrams is to recognize that because this is an exothermic reaction, my reactants have got more potential energy than my products do. So it's not actually an even line here. My reactants would be higher than my products because this is exothermic. Now, there are lots of exothermic reactions like this, and combustion reactions are really good examples. The products have less potential energy than the reactants. It's a downhill reaction. You would think that the reaction should just go, but it doesn't. I've got a stack of firewood out in the backyard, and if I ignite the firewood and I add energy to it, I can get it to burn. And once it starts burning, it's going to keep burning. But at the beginning, it's not going to do that on its own. So what's actually happening there? Why does an exothermic reaction not just happen as soon as the reactants are placed into contact with each other? We have to remember a couple of things. So the first thing we have to remember is if we consider just these reactants first. So these guys are in some kind of a container and they're floating around. They're bumping into each other. The theory of how a chemical reaction actually happens is called collision reaction theory. And collision reaction theory says there are two criteria for having a successful chemical reaction. First of all, when the reactants come towards each other, they must collide in the correct orientation. In this chemical reaction, my products here are going to be nitrogen monoxide and carbon dioxide. So in my products, I'm going to have one of the oxygens from my nitrogen dioxide transferred over to the carbon monoxide. So in order for this guy to pick up an extra oxygen, he has to come and collide with the correct orientation. If this guy comes and collides in like this so that the carbon and the nitrogen run into each other, that's not going to allow this oxygen to be transferred to the carbon. Or likewise, if this guy comes in upside down like this and crashes in like this on this side, or like this, or like this, those aren't going to be what we call effective collisions, where the atom can be transferred and a reaction can take place. They would be ineffective collisions. So what we have to have, first of all, first criteria is we have to have an effective collision. So what we have to have, first of all, first criteria is the collision must take place in the correct orientation. Second thing that needs to be true, second criteria, is when the collision happens, it has to have sufficient kinetic energy so that these things can collide with each other and they're not going to just bounce off of each other and repel, because they have big clouds of electrons around here, and those electron clouds are going to want to repel each other. So I have to collide first in the correct orientation, second with sufficient kinetic energy, which remember that just means sufficient speed in order for these guys to collide. And if both of those things are true, then we will have an effective collision. In order to have that happen, in order to be able to provide enough kinetic energy, we have a little hump. We have to add a bit of energy to this in order to get the reaction to happen. So it's not like we've drawn before where this goes straight down to my products, but I actually have to put a little bit of energy into the system. There's a little bit of a hump here. And this hump here, this guy is called the activation energy. So this difference between the potential energy that I started with of my reactants and this very peak up here, this is called the activation energy. We'll label this E sub A, activation energy. And this is the energy that we have to put into my reaction in order to get up over this hump. And then once we've added that, then my reactants can react and turn down into my products like this. At the very peak here, you'll find what we call the activated complex. Another name for the activated complex would be a reaction intermediate. It's a molecule that forms temporarily in the middle of a reaction that is going to be a transition intermediate between the reactant and the product. Now, the enthalpy change of the reaction is still the difference in potential energy between the reactants here and the products here. The enthalpy change does not include the activation energy. So if I'm wanting to measure the enthalpy change of this reaction, I would be measuring the potential energy difference between the level of my reactants here and the level of my products here. So the enthalpy change is this difference here. This is my delta H, or the enthalpy change of the reaction. So notice it doesn't include the activation energy up here. What if I have an endothermic reaction? For an endothermic reaction, we know already that the reactants have less potential energy than the products. Energy has to be gained by the system in order for the reaction to happen. Is there going to be activation energy here? The answer is yes. As the reaction progresses, I'm not just going to go straight from my reactants to my products. There's going to be an activation energy hump here as well that we have to get over. The activation energy here is greater than in the last example, right? I've got a larger potential energy that I have to gain in order to get to the top. The activation energy will be the difference between the potential energy of my reactants and the very peak, the very maximum amount of potential energy that the system must have. This would be my EA, or my activation energy here. Just like before, the enthalpy change does not include the activation energy. The enthalpy change, or the delta H, will be the potential energy difference between the level of the reactants and the level of the products. So this would be my enthalpy difference for this reaction. This would be my activation energy.